All right, let me get this on. I'm going to try to project my voice, but it's allergy season, and I've been dying the last 2 days. So if you can't hear me, let me know, and I'll try to speak up. There we are. So, as introduced, my name is Bryan Smith. I've been with DataBricks for all of about 5 weeks. I spent the last 10 years at Microsoft focusing on BI and big data technologies. The last 4 years have been focused on open source and big data. And so when we're thinking about how to come and present at this event, I wanted to start, didn't want to go into a big marketing spiel of why DataBricks. DataBricks is a great platform. I hope you give it a try. I hope you like it. And if you do, we can count you as a customer. But I really wanted to speak about Spark in general, because whether you're using DataBricks or Apache Spark, there's still a kind of a foundational code base that's there that you really need to be able to understand. And just in the 5 weeks that I've been over here at DataBricks, already I've seen some fairly consistent patterns that people run into. They're getting started with Spark, and then there's a certain level of understanding around how Spark distributes its processing and its data that tends to trip people up. So we were thinking about getting started. I decided I would go ahead and just switch this up. My apologies to everybody. If my thing will work, it'll switch. You gonna work? You are not gonna work, are you? You are working, but not. All right. My thing's gonna be stubborn. Here we go. All right, we're going to focus on Spark Foundations. So I'm going to switch the title up for you. This is not going to be, I'm coming in cold to Spark. My apologies for that. We are going to assume that you have some base familiarity about Spark. And this being a big data community, I would assume that we all have awareness of what Spark is. And instead, I want to focus on just those rock bottom fundamentals about Spark so that you can then build better applications. Now, I have in the download, and we just updated the link. The original link was just to do some transfer. We reconfigured it to provide anonymous access. You can pull down this deck, and you'll probably want to. There's some embedded videos that'll show you how to set some things up. There's also the data set that we're going to use here, and I'll explain that in just a second, as well as a full-blown workbook demonstrating every single technique that we're describing here with actual code samples against that data set, so you can run through it, see it yourself, tweak things, practice it, and whatnot. That said, I find live demos to be about the most boring way to present for an hour, so I'm going to really speak about the concepts and allow you to then kind of go off and test drive based on that. So, to get started, we will need a version of Spark. Now, if you already have a Spark cluster, you're welcome to do this on your own environment. But if you don't have a Spark environment, you can go to our free DataBricks Community Edition. You just register and you sign in. The video will walk you through kind of what the sign-in process looks like. This is a stripped-down version of what we provide at DataBricks. So the commercial offering has far more features and far more scalability than what you're going to see here. But as a place to kind of test drive small Spark scenarios, it really doesn't get much better than this. So in addition to access to processing resources in a pre-configured Spark environment, there actually are tutorials and other things you can do here. So whether you're a data engineer or data scientist, you can get started very quickly understanding Spark. So once you've got access to an environment, you'll log into the workspace. It'll look something like this. You'll need a cluster. And again, the video will walk you through the basics of setting up that cluster. It's very simple and straightforward. And again, in the production enterprise version that we have in this, there are far more options that you configure to deploy a cluster. But here, because it is a pared down environment, it's a very simple, straightforward process that you can see there. Finally, once you have yourself an environment and you set up a cluster, there is a notebook that you're going to bring on board. So again, the video will walk you through the import process. You'll then bring in the video and you will attach it to that cluster so that you can then do your work against those compute resources. Hopefully that's fairly straightforward for folks. And again, there are the embedded videos to walk you through the entire thing, and hopefully it makes it really easy. If not, shoot me an email at the email address above and we'll get you there. Yeah. It was really easy? Excellent. Cool. Endorsements. Nice. So let's talk about the data set that we're going to use. This is a really fun data set that I love demonstrating concepts on. How many of you guys have played with the UFO Sightings Dataset? So there was this company a while back, and they're no longer in place, called InfoChimps. And they used to be one of the big first clearinghouses for public data sets, and this was one of the just most spectacular data sets they had. It's 60,000 plus some odd UFO sightings. Information about when it was sighted, when it was reported, what was the location, what was the duration, what was the shape of the object that was seen, and then a full-blown description on the end of it. The complexity of the data set and the kind of lack of cleanliness in there makes it really great for kind of struggling with real-world challenges. The reality is none of us get really nice clean data sets to work with. The first thing we have to do is make it workable. And so this is a great example of that. So if you'd like to download it, I put a direct link there. There's also the link, if you download the materials that I linked to at the top of this session, it's in that zip file, and hopefully you can have access to it. The basic data structure looks something like this. It's tab delimited, there are no headers, but the first field is going to be the date that it was cited, date reported, and so on and so on, and hopefully that gets you oriented to it. So when you've got a data set like this, the first thing that we typically do in the Spark environment is we load it into an RDD. And those of you who know Spark and going, what about data frames? Hang on. All right, so RDD, we load it to an RDD. And usually it's with code that looks something like this. So I'm going to read data using the Spark context up from that data file, and now I've got an RDD that I'm calling raw. And then I take that raw and I do a map. A map transform allows me to go item by item inside the RDD collection, apply a function that transforms the data. So I might do something like this, splitting it on tabs, and now my data is organized as a list where I can quickly grab the different fields from there and manipulate the data set. When we're getting started with Spark, this is how we think about our data. Bring it in, and it's this collection that we start interacting with, and just think about ways to apply transforms against the collection. But what you really need to do is you need to understand it not just as a logical structure of the RDD, but how the physical structure of the RDD actually maps out to the physical resources you have available to you. That RDD, the RDD stands for Resilient Distributed Data Set. And the distributed part is the part that tends to trip people up. When you're bringing in items from, let's say, a text file, each line in that text file will form an item inside the RDD. But those items are organized into partitions. The partitions are the units of, or subsets of data that get distributed to the different workers in the cluster. So what you can see here on this cluster is that logically we're working with a construct that we call the RDD, but I might have 4 worker nodes on here, and the different partitions land in different what we call slots on those RDDs. And that's where the work is performed. So why is this important? Well, it's important because we want to make sure that we're taking advantage of all the resources we have available to us to, as efficiently as possible and as consistently as possible across the workers, process our data to get our results. So the first step in doing this is we need to figure out how many slots that we're working with. Now, if you know how Spark is configured and you're digging through the internals of it, you know exactly what resources you provision and whatnot, you can go in and you can more or less figure out how many worker slots you have available to you. But there's also this little parameter that you can pull up that'll tell you. So in this sample cluster that we have here, we have a default parallelism of 8, and that tells me I have 8 worker slots to work with. And what that means to me is that when I'm thinking about my RDD, I don't want to think about it just as this monolithic thing. I want to understand that it is partitioned, and I want to shoot for 8 partitions. If I think about it grouped as 8 partitions, that's going to allow me to take my data and ensure that every single worker slot that's available on the worker nodes in my cluster is being tasked with doing something with this data set. If I don't get it evenly distributed, that means I have empty slots that are sitting there idle and not doing my work for me. And just as an FYI, and you'll see this inside the lab, many of the data access mechanisms we use, like text files, tend to default to a predefined number of partitions, which means a predefined number of slots will be engaged. Text files tend to default to 2. And so what we see a lot of is people going in and provisioning bigger and bigger clusters and going, I'm not gaining anything in terms of performance. Well, it's because you only have 2 partitions, so you're not taking advantage of the resources that are available to you. So it's really important you be aware of how many slots you have and partition your data effectively to get it across those. Now, that said, every worker slot only has so much memory and computational resource available to it, and it is possible to blow out those slots. So if you load up partitions that are too big, you'll get out of memory errors, a really common error that people see. So one of the general rules of thumb, and this is an incredibly general rule of thumb, is that we tend to shoot for about a 200 megabyte partition size max. Okay? So if I have 8 different slots here and I divide my data into 8 partitions, and I say I want my individual partitions to be no more than 200 megabytes in size, and again in the workbook we'll show you how you can actually estimate the size of your different partitions, then that means that I've got, what, 8 times 200? I've got about 1.6, 1.5 gigs of RAM, gigs of data that I can work with. That's not big data. So how do we deal with data sets that are bigger than 200 times however many worker slots we have? Well, we start dividing our number of partitions, or we expand the number of partitions based on the number of slots, so that it's fairly evenly divisible. In this case, it's a really crappy explanation. If I have 8, I might bump it up to 16. If I have 16 and it's still too big, I might bump it up to 24 partitions. If I go from 24, I go to 32. Everything is evenly divisible by the number of slots that I have. Because again, I want an even distribution of my work. Hopefully that makes some sense. Okay. Yeah, so if we've got that, then we have got our data fairly well distributed in a way that our system can efficiently work off of it. There is one more gotcha that does come up occasionally, and so I want to put it on your radar. When we get our data, even the partitions evenly distributed into all the worker slots that we have available to us, in general, the data will typically be evenly distributed within the partitions. You can go in and count the individual items, and you'll see that they're more or less about the same number of items in every side of the partition, though there will be some small variations on that. Certain operations, though, can cause the data to become skewed, so you get situations like this. So I might still define inside my structure that I have 8 different partitions, but some have far more data than others, and some might be flat out empty. And again, I'll show you an example inside the workbook where you can see this in action. And what happens is, in this situation, my data is technically distributed across my different worker slots, but one of these slots, the one here on the far right, is going to grind through that data a lot longer than anybody else, and my application won't be able to move to that next phase of operation until it's done with that. Yeah?
I'm just curious, like, in terms of the number of workers to the hardware side, is there like a zero object across? Is there thinking about that?
In terms of?
How many workers you have versus, like, you can only run this many workers on this, because you have different computers, right? So each one has handle so many workers.
Let me make sure I understand it. So the more computers you bring on board, and inside of DataBricks, we ensure that they're consistently sized machines, because we run in the cloud. It's either going to be an Azure VM instance or an EC2 instance in AWS. All those workers are going to be fairly consistent in terms of the physical resources they have available to them. In general, and this is a very crude generality, one virtual core on that virtual machine is going to translate into one worker slot, but don't depend on that. Always investigate and see what Spark thinks it has. The reason I say that is certain size virtual machines, we might approach the worker slot sizing a little bit differently, so we have our own algorithms for that. And also, in DataBricks, we use elastic scaling. So based on the actual demand that we see, we will add resources and subtract resources in your environment as kind of a cost control mechanism. So you don't really want to come in with kind of a fixed mindset. You always want to programmatically determine how many workers you have available to you, hence that little default parallelism. Yeah. But if you understand the algorithms and you're willing to dig through a little bit, you can more or less figure out what you should have. But the big thing here is we want to be aware of item skew within inside of our partition. It does crop up occasionally, and it can mean that some workers, even though they have partitions assigned to their slots, are sitting there idle while others are being overtaxed, and that's a huge bottleneck. Okay, so this is a distributed part of the RDD, the Resilient Distributed Data Set. So let's look at how work gets assigned to the different partitions, because that is where the work is performed in these worker slots. And so to do that, we're going to introduce a little bit more code. So just like before, we're going to read our data in from our text file into an RDD that we're going to call raw. Now, just so that I don't have to make these incredibly elaborate diagrams going forward, I'm going to say that we had 4 slots instead of 8, and that's going to help me strip these things down a little bit. So I'm going to go ahead and say, hey, I've got 4 slots, and therefore divide this into 4 partitions. Okay. Then what I'm going to do is I'm going to go through each item that I read in. I'm going to split it. Each line should be tab delimited, so I'm going to split it on those tabs to allow me to access my data. And then I'm going to use another call to the map transform to extract the year off of the date of the sighting. I will then filter this data set so that I'm only grabbing those sightings that are 1990 and later. And that's because this data set didn't start getting developed until 1990, and so while there is some historical stuff that's in there, a lot of the older stuff is kind of garbagey compared to everything else, so 1990 is a good cutoff for this. So if this is my logic for accessing this data, let's look at how that logic is applied to those partitions. So we have our raw RDD. Let's assume we've gone ahead and we've read it off of the file into our 4 partitions. Again, we were using 8 before, but 8's too many boxes to have on here. I take that raw RDD and I apply the map to split it based on the tab. And again, pseudocoding here just for being a little bit easier to look at. I get, in theory, a temporary RDD under the covers that's holding that split out data set. I then apply the extraction of the year and tack that onto my data set, and then I apply my filter to arrive at my sightings RDD. So when you read the documentation around Spark, it talks about every single transform creates a new RDD. And in our minds, this is how we think about this process working. That's not actually what's happening under the covers, and this is really important to understand, as you'll see in just a second. What's actually happening is Spark is smart enough to recognize that the map here, and the filter here, there's a narrow set of dependencies here that we are working with. So this partition right there, where in the middle, is dependent on data that was in the partition that preceded it, right? As this is dependent on the partition that preceded it, and this on the partition that preceded that. There's a line of processing where there's a set of dependencies here in that sequence. But nowhere in there does a partition have to have awareness of data in its neighboring partitions, right? Each partition, it can be processed in sequence, flowing from left to right without any knowledge of the other 3 partitions that surround it, okay? Because they don't have to have knowledge of data in those other partitions, what the Spark engine is able to do is able to take that sequence of those 3 operations and collapse them down. And saying, you know what, we're gonna go from the raw RDD to the sightings RDD in one shot. Those 3 steps, because of the lack of interdependency between those partitions, can just be sequenced in one operation to create that new in-memory structure, and there we go. And when you're looking at the Spark UI, you can actually see this. There is a visualization we call the DAG visualization that'll show you this. So if you're looking at the DAG visualization, that first dot represents your sourcing of the data from the text file. The data from the text file flows into an RDD, and then down one more, and there we go. So source to our raw RDD, those 3 transformations into here. Now, unfortunately, when you look at the DAG, it doesn't explicitly tell you those things. This is one of those things where you kind of have to go add some logic and tweak it and see what it's doing, and you kind of figure out what's going where. But whether I had this one, 2 of these, or 3 of these, that DAG is going to be unchanged in terms of representation. It's collapsing them all down to give me that result. Okay, so let's add a little bit more logic to our sighting stuff. So we've gone here, we've read our data out of our data file into the raw RDD with 4 partitions. We've split each of the lines that's coming out of that data file based on the tab delimiter. We've extracted the year, and then we filtered for data that is 1990 or later in terms of the sighting date. We now want to go in and we want to calculate how many sightings do we see on a per year basis. So to do that, I'm going to use this reduce by key transformation. Before I do that though, the reduce by key does expect that my data is structured as what's called a pairwise RDD. Basically I have 2 values. The first is what we call the key, the second one is what we call the values, whatever we want it to be. In this case, we're just going to use 1 as our value, but the year is going to serve as our key. And then we'll go and sum up the number of sightings in those given years. So this is our flow up to that by year. So we're going to take our data into the raw RDD, we're going to split it, we're going to extract the year, we're going to filter on it, and now we're at our sightings RDD. We do have to restructure our RDD to be a key value pair. And because of that, even though that's still a narrow transformation, because I'm slightly adjusting the type of my RDD, Spark will actually add an additional step into its processing logic. Now I have this unnamed RDD that's sitting there in memory, and I need to get this over to a structure to do my reduce by key. And here's where it gets interesting. At this point, my data is scattered all over the place. I have data for 1990, possibly in every single one of those partitions. I have data for 1991, also possibly across every single one of those partitions. What I need to do for the reduce by key is I need to get all the data for the same years into the same partition, which means now that I have to have awareness of what data sits inside my neighbors. And this is going to trigger an operation that we call a shuffle. Shuffles are expensive. Shuffles require data to come out of a partition, be reorganized, and then redistributed into a new set of partitions. This actually serves as a boundary inside of our processing in that Spark has to bring everything to a head, get all the data redistributed, and then start processing again. This is one of the biggest challenges we have in any distributed system is dealing with that data exchange. So we want to be really, really aware of when we're triggering these things. Inside the DAG visualization, you can see it like this. So here is our original one where we're reading it from our text file, and that lands here. So now I have my raw RDD. I apply my 3 initial transformations there, and then I transform it into a pairwise RDD. Again, this all occurs as a single line, and you can notice by the red box that this represents a single stage of operation. Here, this little line that goes over here to another red box, that represents the shuffling of my data. That's what's occurring right here. So whenever you see these boundaries, these red box boundaries coming up and crossing across it, that's representing data going between the different partitions. Once it's distributed, then processing continues from there to do my reduction to count the number of sightings per year. All right. So what are our big concerns with this? Again, shuffles require all the processing to come to a head before we can then start interchanging data. That interchange of data has a certain amount of network overhead, but also has a lot of disk overhead. When we do the shuffle, the data is actually written out to shuffle files on disk before it's then exchanged between the different nodes. So as much as we talk about Spark as being an in-memory system, this is a place where we start to incur disk I/O, and disk I/O is usually problematic for us. Then we have the added benefits of a shuffle that when we do the shuffle, there is potential that the number of partitions that we have in our resulting data set has changed. So we may have been very aggressive at the top of saying maybe I have 4 worker slots here, and so I'm going to partition it by 4, but I get to the other side of the shuffle and now I have 2. Or I might have had 8 and it brought it down to 6 or 4. There are different algorithms for determining that, and it doesn't typically change, but there are scenarios where it does. So this comes a place where I now need to go back and revalidate my partition count. Also, when I'm doing my redistribution of data, if my data is heavily skewed around my keys, it is possible that I get back to a situation where the data inside my partitions are themselves skewed. Again, there are algorithms that are there that are trying to balance that out, but if the bulk of my data was, let's say, 2008, and there are only a few sightings for all the other years, and I divide it across 4 partitions, I might end up with a big bloated partition for 2008, and everything else is kind of small and skewed downward on the others. So we need to be very, very cognizant of that shuffles not only are problematic from a performance standpoint, but can create imbalances that we need to go back and correct. So the general guidance on shuffles is when you're incurring operations or you're applying transformations that incur a shuffle, you need to be aware of these things. You need to go back in and try to minimize the frequency with which these occur, and there are some tricks that you can use for that. We also need to go back and validate that everything is still in a good state after having done this. All right, so cool. We've got our data now loaded in. We've calculated the sightings per year. We then want to do something really, really crazy with this. I've got my original sightings data, and I've gone in and calculated the number of sightings per year. And what I'd like to do is take my raw sightings data and split it out. I'd like to find those sightings data that were associated with years that I consider to be kind of low in terms of the number of sightings. And I want to go back and get my data separated out for the sightings associated with years where there are a high number of sightings. And this is one pattern that I could use for this. I could come into here and I could join my sightings data back to my by year data with some simpler filtering on it. Of course, to do the join, I do have to have my sightings data structured as a key value pair, so I'll do a little restructuring here before I flow into the join. There's a lot going on there, and again, if you're new to Spark, this one's a little bit overwhelming, but here's the main thing I want you to take away from this. This is the execution plan that we end up under the covers. This is what the DAG visualization looks like. And when we look at that, a couple of things should jump out. You may notice that this left-hand box and the first part here look very similar. And if you think about it, what we're doing is here, we're taking data and we're reading it from a file, we're applying those 3 transformations, we're doing a couple other things before we then throw it over here, and that's where we're calculating the by year stuff. I have to read my original sightings data in here and restructure it in preparation for a join which occurs there. This and this are pretty much the same thing. So those represent redundant paths of execution. both sourcing from the same place, applying the same transforms to then kind of flow into different parts of this logic. This provides me an opportunity. I can look at this and say, instead of performing that same work twice, what I could do is I could say, hey, perform the work once, read it into that sightings RDD, which is basically this part right here and this part right here, and cache it. When I say cache it, what it's going to do is it's going to process the data up to that point the first time, and then it's going to pin it in memory. And anybody else who needs to execute that same flow of logic is going to use the cached copy for me to minimize the work. And when I do that, what's going to happen is on my diagram, it's going to be a little hard to see here, I'm going to see those spots that represent my cached data coming up with little green dots. Now again, the first time I execute this, it does have to go back and do the original work to populate the cache, which means that from here to here, that's actually being run in just like it was before. But here to here, it's going to piggyback off what was cached over there. Yeah?
I'm not quite following. So I understand everything up to where you're doing the old cache.
Yep.
Like why is it that you have to, why do you have to have the same flow there?
Okay. So what we did here, so the question was, why are these redundant paths? So what we've done inside of our base data set, again, when you go back to the notebook, you'll see this in a little bit more detail. We read the sighting data in. We prep it so that we're filtering out data that occurred prior to 1990, right? And then we kind of pause right there. From there, we might go off to the side and calculate the total number of sightings in a given year. And that's what you're seeing right here. Okay, that's that shuffle that we saw there before in the previous diagram. Or we might take that structure of data and restructure it as a key value pair that's going to allow me to flow into the join right there. But fundamentally, that and that are an identical set of work. Okay? And so what I might do is decide that that's a really good spot to go ahead and cache my data. Now, there are other places I could have cached my data inside of here and gotten some value out of it, but what I want to be cognizant of is that when you cache things in memory, and that's the default mechanism for caching, you are taking resources away from your environment that it could be using for other stuff. And so it's a real balancing act. How much am I gaining by pushing this in there versus losing in terms of resourcing? There's no hard guidance on what the right balance is. It's one of those things you kind of have to play with. But the more I bring into memory, the closer I get to a situation where I could potentially have an out-of-memory error, and that's what I'm trying to avoid. Okay? So the big thing in here, what makes me feel that this is a good spot to go ahead and cache this, is not only with inside the single flow do I have a redundant operation. If I go and calculate my second data set, which is the sightings for the high sighting years, it's identical here. So what's going to happen is, by caching this in one spot, this first one's going to run, it's going to cache, and even in the execution plane, it's going to be able to use it again. But this guy over here, because it's also based on that sightings RDD, is going to be able to use that same cache as well to accelerate its work. Okay? So we want to think about when we're running, especially any really expensive data processing operations, we want to think about, is there potential for the reuse of the data set that I've assembled, and take a look at caching. Again, we don't want to over-cache, and we see a lot of folks doing this, of just aggressively caching everything. You want to be really selective about how you go about it, but when there is a lot of redundancy, and when there's a lot of work that leads into that point of redundancy, that typically tells me that's a good place to think about employing cache. Yeah?
Is that cache played in disk?
It can. By default, it goes to memory. You can configure it to say memory or disk if there is memory pressure. What starts to happen is you start to use some of the non-memory options, the performance benefits of it start to degrade. There are some things that keep it in memory, but with a smaller footprint because it's been restructured. And of course, when you access it, you have to convert the structure back into the usable form. If it goes to disk, you have to pull it back up into memory. There are, I think, like 6 different caching variants, and each of them is a trade-off in terms of memory footprint and performance gain. If it was something, let's say the sightings RDD took me an hour to develop, to process, and you'll notice this is a small data set, so it'll take seconds to run. But if it took hours, spilling it off to disk and incurring that hit might be a good choice, but it just depends. We tend to prefer in memory. So as you're getting started with Spark, these are all the big things that you need to think about. How is my data being partitioned? Do I have that aligned so I can take advantage of all the resources in my environment? Is my data distributed evenly across my partitions? As I'm doing work on my data, understanding that work is being applied to partitions, when do I encounter situations that might require the creation of a new set of partitions, and then how might things get out of balance there? And we have to manage that. And then finally, as I think about some data sets, the partitions could be reusable, I can use caching to kind of minimize some of that redundant execution. Those are all the things that we need to be aware of. Think of this as like the really early days of relational databases. Any of you guys old school Oracle DBAs or anything like that? You used to have a really deep knowledge of how the internals of the engine worked. As much as we are trying to mature and progress the technology, the reality is Spark has only been around since 2013, right? And it hasn't been publicly commercially available since I think it was 2014. So this is still a fairly immature technology where you have to have awareness of the internals if you want to do big stuff. Now, all that said, we do have higher level constructs that we can work with, things like data frames. And we strongly want to encourage you to move towards these data frames and other higher level constructs whenever possible, simply because those things have algorithms built into them that understand many of the mechanics that we're talking about here and will very aggressively try to address many of the problems that we're seeing. But they're not perfect, and they're not foolproof. And fundamentally, those higher level constructs all are being executed on base RDDs using the fundamental patterns that we've talked about here, where you have to, if you really need to troubleshoot something, go look at those DAG visualizations just like we saw there. So there's no escaping it. You gotta know the old school stuff or it'll come back and bite you, okay? So, cool, some people get the reference, nice. Cool, so any questions about all this? Just stunned silence. That's how I like to leave an audience. All right, well, hopefully you'll get a chance to download the materials, take a look at the deck, get yourself an environment set up, upload that DBCC, and go through step by step and take a look at some of the stuff in practice. There's a lot there to digest. So as you're going through that, if you have any questions, feel free to reach out to me. My email address is up there. All right, thank you. Oh, yeah.
Can you address Spark streaming just for a moment?
It's a thing. Spark streaming is not my area of expertise, but Spark streaming fundamentally works off this stuff. It's just populating an RDD based on a clock and maintains not only a cache for data coming in, but also a cache for based on the windowing that you define and reconciles that. So fundamentally it works very, very similar to what you're seeing here, but there are some differences. So that's about as far as I can address it right now. 5 weeks, buddy. Yeah.
Can you cache multiple things, or are you limited to one cache per
Gotcha. So the question was, can I cache multiple items? And the answer is yes. You could go in and cache every single RDD, and we do see people do that. It's not a recommended pattern. What we want to encourage you to do is think very, very selectively about where am I going to get the biggest bang for the buck. That's the key. So looking at your DAG visualizations, understanding what's the work that's being repeated, what was the cost of doing that work? And again, we're showing some things here with this small data set. Nothing here was terribly difficult or expensive to compute. But as you get to bigger data sets, you'll want to have that knowledge and awareness and have to scrutinize it and say, you know what, that's where I'm willing to take the hit. And then it's just, look at the consequences. The more I put into memory, the closer I get to that really problematic and hard to troubleshoot out of memory error. Again, we can back off with different caching mechanisms, but we start to trade performance for that, and it's a real juggling act. Yeah. Cool.
Is there a way to, I don't know if you have this in your system, a way to clear the cache?
Yes. So the question was, can we clear the cache? So let's say we had a really long script that we were running, and there was a lot of redundant execution at the top. But once I'm past a certain point, I'm no longer having to go back and revisit that stuff. Instead of keeping things in memory, you can call the unpersist method on that RDD, and it says, okay, I'm no longer need this for cache, go ahead and release it, and those resources then come back to the environment. Yeah.
So as you code, as you're coding, it's pretty much sequential.
When you're coding, is it sequential?
Yeah.
Yeah, so this is one of the weird things with Spark. Yeah, so the question was, is it sequential when you're running things? And the answer is no. And this is where you have to be really, really cognizant of what your application does in its entirety. So when you write a series of transforms in Spark, nothing's happening. You execute it, and it basically acknowledges the syntax was valid and cool. I got the instructions. I've got the instructions cached. It's not until you encounter what's called an action. And so you'll see this inside the script when I'm using to take or collect to retrieve data and spill it back to screen. Actions also occur when you spill data to disk, like you're going to store it. There are other things that can trigger actions as well. And what happens is when an action occurs, the Spark engine goes back and says, cool, you've called an action on this RDD. Where'd that RDD come from? And it works its way back up through the logic to figure out what are all the components that would have to be executed in order to allow me to then execute this action. And those are the only things that get called. And so if anywhere in there you had a cached data set, it could say, hey, up to this point, I've got a cached data set. I don't need to go any further. I'll just take it from the cache and move forward. But if you didn't have that, then it would need to go back and work us all the way back up to the sourcing of the data. Yeah. Cool. Any other questions? Guys, well, thank you very much for having me out here today. I hope this was helpful. This is definitely not a getting started like it was advertised, but hopefully as you are getting started, these are things you'll see in the literature, you'll have a little bit more awareness about it, and it'll help you avoid some of the big stumbling blocks that we see a lot of people encountering. All right, thank you very much.